MMAPV1 grew from the original MongoDB storage engine. It's called MMAPV1 because it makes use of the mmap system call in Unix to map the files on disk directly into virtual memory space. This lets us treat the data files as if they were already in memory. If they're not already in memory, a page fault will pull them into RAM, and if they're in memory and we update them, an fsync will propagate the changes back to disk. So why was this used as the original storage engine? Well, this decision was made when MongoDB was still young. And by still young, I mean still young as a company. It was known as 10gen then, but also still young as a database. And memory mapping the data files allowed us to focus on features and pushed much of the work of writing and reading BSON to and from the hard drive onto the operating system. The mmap storage engine grew from the seed of that initial design decision, as you'll see shortly. But first, let's talk about how to use it. So MMAPV1 is the default storage engine in MongoDB 3.0. But you can also use -- storage engine mmapv1 to invoke it. Let's take a look. When I run MongoDB with -- storage engine mmapv1, I can see explicitly that the storage engine is mmapv1 in the logs. If I don't explicitly specify the storage engine when I run my server, it won't be obvious in the options document. However, I can still find out what my storage engine is by connecting with the shell. I run db.serverStatus, look for the storage engine, and there it is, mmapv1. Let's talk about some things to keep in mind with MMAPV1. The first is that MMAPV1 comes with collection-level locking as of MongoDB 3.0. Prior to that, it had database-level locking with 2.2 through 2.6. The granularity of the locks are worth considering because they may or may not affect performance depending on your setup. So let's talk about them. First thing to consider is that locking is about shared resources. So what do we mean when we talk about shared resources? The most obvious, of course, is data. If two processes are attempting to write to the same region on disk at the same time, corruption can occur. For this reason, MongoDB has a multiple readers, single writer lock. What this means is that you can have as many readers as you like, and they will lock out any writers. As soon as one writer comes in, however, it locks out not only all readers, but all other writers as well. If data were the only issue, we might have document-level locking. But the reality is, there's other information, specifically metadata, where conflicts can occur. For example, two documents located at different places on disk might share a single index, so an update to one document will also involve an update to that index, and an update to the other document might involve an update to that same index, causing a conflict even if the documents are widely separated on disk. Another example of something that might cause a conflict is the journal, which we'll talk about shortly. You'll note that prior to MongoDB 3.0, you had database-level locking. So, if you're able to distribute your load on the server among multiple databases, you can have simultaneous writes without any conflicts. With MongoDB 3.0, you have collection-level locking, which allows for more flexibility. Even if you have multiple collections in the same database, you can still write to them simultaneously until such time as you're fully utilizing your resources. This allows for more flexibility. Keep in mind that even if you don't have sufficiently granular locks, this is an issue that you can scale your way out of. Even if all of your documents are on the same collection, you can shard that collection, we talk about sharding in another section, and distribute your load among multiple servers who can then independently, simultaneously perform the writes. This isn't ideal, but it will work. The next thing to keep in mind is the journal, which is a write-ahead log. Why do we have this? To ensure consistency. Think about what would happen in the event of a disk failure during an fsync without this. Some bits might get updated, others not. With the journal, you write down what you're about to do, then you do it. So if a disk failure occurs while you're writing to the journal, that's fine. You simply don't perform the update. When the disk comes back up, it notes the state of the database, notes that there was a partial update logged in the journal, but not a complete one. It ignores that log, and your database comes up in a consistent state. If a disk failure occurs later while you're syncing your data to the disk, that's fine too. You've got it complete in the journal, and when your system comes back up, you note that there was an incomplete update on the document, you look at the journal, complete the update, and the database is back in a consistent state. So journaling is what ensures consistency of the data on disk in the event of failure, and we strongly recommend it for all production systems. Finally, keep in mind with MMAPV1 that data on disk is BSON, raw BSON. So bits are mapped from disk to virtual memory directly. This has implications for data modeling, as we'll discuss in another lesson.